Okay. For this lecture, we're gonna talk about solving the wave equation in 3D and 2D. I wrote down the equation here is equation 1. Basically, it's just a basic wave equation, UTT equals to Laplacian of U. And we are given two initial conditions because we have two derivatives in time. So we are given that ux0 equals to g of x and ut of h0, x0 equals to h of x. And we're gonna work with eventually the cases in which the dimension is 3 or 2. And we have already talked about spherical means and the way to approach it, but for consistency, let me recall quickly this definition. So definition of spherical means. The idea is simple, right? I mean, the point is that we fix x and t a priori in Rn times 0 infinity. And then think about it is that if you are given a point x in Rn, think about wave propagating with speed 1 after an amount of time r. It can propagate within the ball of center x radius r, right? And the sphere around it is the sphere of center x radius r2. And that leads us to the definition. Remember that the key point here is that x and t are fixed. And we define, we set capital U of x rt to be the average of the integral within the sphere of center x radius r uyt dsy. Okay, so we are taking the average of integral on the sphere that I'm highlighting now. Okay, and similarly for the initial conditions, I denote by g of xr because there's no t to be the average of the integral on the sphere of center x radius r g of y dsy, and h of xr, so the average on the sphere of h. Okay, so there maybe two key points here that I want to highlight on this sort of definition of spherical means. The first key point is, of course, by the mean value theorem. We do have that intermediate value theorem. We do have that limit as the radius r goes to 0, capital U x rt equals to little u of xt. So basically, through spherical means, when we let the radii tending to 0, then we recover the function u itself. And similarly, limit as r goes to 0 of g of xr goes to little g of x, and limit as r goes to 0 of h of xr equals to little h of x. Okay, that's the first key point. The second key point is that, this is sort of already done, but this is coming directly from thinking about Laplacian in spherical or polar coordinates, that we can see that the Laplacian in polar coordinates or spherical coordinates. So I can say this is first key point. Second key point is that the Laplacian in spherical coordinates take the form of urr plus n minus 1 over r times ur, right? I mean that's we have seen already when we did the fundamental solution for the Laplace and the heat equation, and it appears again here. And in fact, this was already done, and it's evidently clear that we have that, this was the lemma done last time. Let me recall it. It's the lemma 1, that you fix an x because x is fixed here. It's not a problem. Then we would have that because x is fixed. You can see that now we can think of u as a function depending only on r and t, right? Because x is fixed. So for simplicity, I will write just that u depends on r and t only, 0, infinity, cross 0, infinity to r, mapping rt to u of rt. And indeed, this is actually uxrt, but I just didn't mention x for simplicity. Satisfy the wave equation. I mean, modify wave equation in the first quadrant. Okay, let me write down that I would have the equation 2 here, that utt would equal to urr plus n minus 1 over r times ur. So it's not exactly the wave equation, it's a modified wave equation because we have this n minus 1 over r times ur, right? So this satisfies in the first quadrant, 0, infinity times 0, infinity. And we would have that u r u of what u of r0 equals to g of r, and ut of r0 equals to h of r on 0, infinity. Okay, so let me highlight it here that again, this is not exactly the wave equation because there's a additional term, but at least that, by doing spherical means, we have been able to reduce the complicated wave equation in n dimensions to a modified wave equation in the first quadrant. First quadrant because we are only dealing with here that, r and t. We are only dealing in this first quadrant in which that r and t are greater than 0, right? Okay. Now our purpose is sort of like using this modified wave equation in the first quadrant, trying to solve it, and then coming back to, coming back and use this first property. Once we have u of rt, we can let r goes to 0 to recover uxt. Okay, so that's the idea. Now it turns out that we can do the next sort of point is gonna be that we try to do some change of variables, or I can say that in general it could be some ODE trick to transform equation 2 into the usual wave equation in the first quadrant. That we know how to solve by previous lectures. And it turns out that this trick works well. So I can say that the tricks work well for n is odd. So it works well for odd dimensions, which is kind of interesting. It doesn't work well for even dimensions, and we need to use a different trick. Okay, so let me now proceed to solve the equation in 3D, in which means that in case n equals to 3, and then we will solve the equation when n equals to 2 later. Okay, so let me do the case n equals to 3. This corresponding to the so-called Kirchhoff formula. Okay. All right. So let me so when n equals to why did I put capital N? When n equals to 2, the equation 3, sorry, equation 2 becomes, let me just write out the equation without the initial conditions. I would have UTT equals to URR plus 2 over R times UR. Okay, and now the ODE trick kicks in, essentially that we're going to try to combine these two, combine this into just a single term. Okay, it's always some ODE tricks that we can sort of put things together. And in this case, I realized that there's a 2 here, and a natural idea would be, you know, like would be multiply both of the size by R. I would have R times UTT equals to R times URR plus 2UR. Okay, and then I would realize that the right hand side here is nothing but exactly you know, how do I say it? It's nothing but exactly R times U differentiate twice in R. Okay, so let's double check. If I take R times U differentiate twice in R, what do I have? If I differentiate once by the product rule, I have R times UR plus UR. U, if I differentiate in R, it becomes 1. So R times UR plus U, or differentiate in R. And then I do it the second time. Then I use again the product rule for the first term here. I would have R times URR if I differentiate in UR. If I differentiate in R, I have 1, so plus UR. And then the last term, which is UR. So it exactly R times URR plus 2UR, which is really beautiful. And hence, this really already uses the key that by defined you tutor, again, it depends on X, as I said from the beginning, but I mean, I'm fixing X. So I define U tutor RT to be R times U of RT. Then clearly, I would have U tutor of TT equals to U tutor of RR. So it does really solve the wave equation in the first quadrant. And moreover, you know, because we define U tutor of RT equals to R times URT, we do have that U tutor of ZRT equals to 0, which is really remarkable. So now let me put everything together. I would have the equation 3 that U tutor satisfy. That is, I have U tutor of TT equals U tutor of RR in the first quadrant. So in 0 infinity cross 0 infinity, U tutor at R0 equals to G tutor of R, which is defined to be R times GR. Okay, UT u tutor t at r0 is equals to h tutor of r, which is defined to be r times h of r. And moreover, at the boundary, the other boundary of the first quadrant, I would have that u tutor of 0t equals to 0. Okay, so let me draw a okay here. I have the equation inside here. And I have that in this boundary, we have u tutor equals to g tutor and u tutor t equals to h tutor. And on the other side of the boundary, this boundary, that we have that u tutor equal to 0. Okay. So we do have this, and then you can see that we can do I mean, we did it earlier. I just say that we can perform odd reflection to solve the problem, right? And we get the formula that, by abuse of notation, I'm still writing the odd extension of G tutor and H tutor to be exactly G tutor and H tutor. So the formula we get is simply that U tutor RT would be equals to, I mean, the formula we are using is exactly the D'Alembert formula, right? That is 1/2 of the value of the initial data from the left and the right, which is G, wait, what? G tutor of R minus T plus G tutor of R plus T, and 1/2 of the integral of the velocity from R minus T to R plus T. Velocity is H tutor of Z dz. Okay. So that's the D'Alembert formula, in which that I'm by abuse of notions that notations that I'm using the odd extension of G tutor and H tutor to be exactly themselves. Okay. Now, what do we want from here? So from here, we have that. Okay. U of RT is nothing but U tutor of RT over R. And the key point was, I noted here, let me recall. The key point that I noted here is that in order to recover little u at xt, I only need to take the limit of the spherical mean as r goes to 0. So what it means is that I can use this, and then I can use the fact that little u at xt is nothing but limit as r goes to 0 of u of rt, which is limit as r goes to 0 of u tutor rt over r. Okay, so that's the point that I can use the above formula and this relation to get back the formula of little u. So maybe I can tell you a little bit. I can draw a little bit of the schematic positions of those. So this is a real line. This is 0. I have t is some positive term here. Remember that we are taking little r going to 0. So when little r goes to 0, what does it mean? When r goes to 0, that means that r plus t is quite close to t, okay? And this is gonna be r, t minus r is also close to t, but this is minus t. This is minus t. But the point is that the point of r minus t is somewhere here, right? R minus t is negative because r is going to 0, so r minus t is approximately minus t. Hence, if you check this formula here, we need to do the odd reflections in order to make it back to the results that we want, right? I mean, this was already noted when we solved uh, um, the wave equation in the first quadrant, but it's good to recall it here, that we see that for t greater than 0, as r goes to 0, we see that, we always do have that that the because r goes to 0, right? So we would have that 0 is less than r, less than t, and thus the formula u tutor of rt can be reduced to the fact that we use odd reflection to reflect that the g tutor of r minus t to be g tutor of r plus t is the same. The g tutor of r minus t is being odd reflected to be g tutor of t minus r. And same for the integral, it becomes integral from t minus r to t plus r h tutor of z dz. Okay. Now then I can write out the formula. Then we have simply that uxt equals to limit as r goes to 0 of u tutor of rt over r, which is limit as r goes to 0 of 1/2. Let's put them together, the one, two together. Of g tutor of t plus r minus g tutor of t minus r over 2 times r, right? I have 2 already, and then divide by r plus 1 over 2r integral from t minus r to t plus r h tutor of z dz. Okay. You can see now that the first term in this limit is nothing but exactly by definition, the derivative, right? That's a derivative of g tutor at t. Yeah, it's beautiful. It's precisely the derivative. And the second term, I have the length of the integral from t minus r to t plus r is 2r, and I divide by 2r. I take r goes to 0, so that's exactly the average of the integral as r goes to 0, right? And the average is, this is exactly the average of this integral, and h tutor is a continuous function. So the average would goes to exactly the value of h tutor at t. Okay, so we have that beautiful formula. Okay, so we conclude uxt equals to g tutor prime at t plus h tutor of t. And if you recall, g tutor prime at t is what? G tutor is defined to be r times g, right? So it's and this is t, sorry. So no, it's correct, but this is t times the average of the integral on the ball of center x, on the sphere of center x radius t, because t equals to r, of g of y dy differentiated in t. Maybe better to write differentiating in t. And plus h tutor of t is nothing but, by definition, just t times the average of the integral on the sphere. h of y dsy. There's a typo here. Okay, now we have that formula. And you know, when I differentiate this integral with respect to t, I have t appears either in the t terms or in the sphere of radius t, right? So we need to be careful. We can do it this exactly like what we did earlier, that we change the variable to make the sphere of radius t to be the sphere of radius 1 and differentiate. Um, um, so I mean, everything is quite straightforward. So let me just state the theorem for you. So theorem 1 for today. One is that wave equation in R3, that is when n equals to 3, and this is the Kirchhoff formula. That you know, we have let uxt be this formula. Let me write out this formula, and then I also write out the formula when you do the differentiation directly. Differentiate in t plus t times the average of the integral here, h of y dsy. Okay, if you hit the derivative in, it turns out that we have two terms. Either you have the average of the integral bxt gy dsy, right? Because you hit the derivative in t, it becomes 1. Or if you hit the derivative inside the sphere of radius t, by doing the change of variable, you can realize that this is exactly equals to dgy dot with y minus x dsy. And then the last term is just the same, hy dsy. Okay, or you can just combine them together, which is the average of the integral in this sphere of center x radius t gy plus t times dgy dot with y minus x plus t times h of y dsy. So let's uxt to be this, then you solve the wave equation 1. Okay, so that's a theorem for the 3 dimensions. It, you know, it looks complicated, but you know, it's really like, let me repeat that first. We do the spherical means to reduce the wave equation in n dimensions to be, you know, like a modified wave equation in the first quadrant. And then in the case n equals to 3, or in general for the case of odd dimensions, we can do another change of variable. In this case, we let u tilde equals to r times u. After this change of variable, we get back to exactly the wave equation, the original wave equation in the first quadrant, and we use the odd reflection to solve it. After doing the odd reflection to solve it, we then let r goes to 0 to get back to the formula for uxt. Okay, that's the approach. Um, and and there's one point I want to make a remark. We will come back to this, but a remark here that is quite important. Remark one here is that you can see that the solution of uxt only depends exactly on the informations of the initial data on the sphere, right? Uh, you know, so let's say uxt only depends on g and h on the sphere of center x radius t. Okay, so it doesn't depend on the initial data anywhere else. So in other words, you can see that, let's say that you are at the point x in time t. What determines the information of you? It's only the information on the sphere around you, the sphere of radius t. So only the information around that, it takes time t to approach you, and it gives you exactly everything. Okay, so that does that. We come back to this, and you see why did I emphasize on this. Okay, now let's do the second part of the lecture, and what did I call it? I do 1 or 2. Oh yeah, I just say the case any case. Okay, now let me say that it's the second case, which is the case n equals to 2. So it's exactly the case of wave equation in 2 dimensions. This is the corresponding Poisson's formula. Okay, it turns out that for the wave equation in 2 dimensions, we cannot, let me write it down. Then the equation 2 becomes UTT equals to URR plus n minus 1 over r, right? In this case, it's 1 over r UR. It looks pretty much the same like the previous equation. I mean, there I have 2 over r, and here I have 1 over r, right? So one might wonder, why do I separate them to 2 different cases? Why don't I consider 2 of the cases the same? But it turns out that there's a very weird phenomenon going on here, that if if I consider even dimensions, or in this case just n equals to 2, I have URR times plus 1 over r times UR. I cannot do any trick to do the change of variable like earlier to get to this reduced to the user wave equation. Maybe let me give you a try here, so that let's try to do some change of variable to get to the usual wave equation. Like earlier, the way that we would think about it is that we would try to multiply r to the alpha to both of the sides, right? R to the alpha times UTT equals to r to the alpha URR plus r to the alpha minus 1 UR. Okay. This is a try. I'm just trying to do it to show you that it doesn't work. And then we would define u tilde equals to r to the alpha times u. Then surely u tilde tt equals to r to the alpha times u tt. No problem with that. Now let's compute u tilde rr, right? Let's compute it slowly. And u tilde of r equals to, if I hit the derivative in r to the alpha, I have alpha r to the alpha minus 1 times u plus r to the alpha times ur. Okay. And then let's do it once more. If I differentiate once more in r, I would have that by using product rules again. Alpha minus 1 r to the alpha minus 2 times u. That's the first term. The second term is that when I hit the derivative in u, that I would have alpha r to the alpha minus 1 times ur. And these same terms appear if, so that's it for the first term. For the second term, I also need to use the product rule. If I hit the derivative in r to the alpha, I have exactly this term appears once more. So I have 2 here. And if I hit the derivative in ur, I would have r to the alpha urr. Okay. So you see that I have u tilde is this one. Let me put a box around it. I need to match it with this one. Okay. These two have to match, right? And well, for it to match, you can see that I have this term, that the first term here that I'm highlighting here, it doesn't appear in the first box. And in other words, what I need to expect is that, I mean, I need it to go away, right? I need alpha times -1 have to be 0 in order for it to go away. Okay, so if alpha, you know, so that would mean that I have either alpha equal to 0 or alpha equals to 1. Okay, if alpha equal to 0, then I would have 2 alpha r to the alpha -1 ur would equal to 0. So this doesn't match with r to the alpha -1 ur, right? And if I take alpha equals to 1, then I would have 2 alpha r to the alpha -1 ur would be equal to 2 r to the alpha -1 ur. And this also doesn't match with the above term. So either way, it doesn't work. And that's sort of why that, the trick of doing the change of variable earlier doesn't work. So earlier trick doesn't work, unfortunately. Okay, so this is a failed try, but this is important to try. Okay, I would say that this is failed. Okay, then how do we handle it then, right? I mean, it is, if it's failed, then how do we handle it? Well, one way to handle it then is sort of now use the approach of, lifting the problem from 2D to 3D. So basically, what we're gonna do is that we're gonna introduce a fake variable to make the problem from 2D to 3D. In 3D, we already have the Kirchhoff formula. And then we get rid of that fake variable to get the problem back to 2D and get the formula. Okay, so this is the approach. Then a correct approach. It would be that we are in 2D, we introduce a fake or an additional variable to get to 3D. Okay, so in 3D we do have the Kirchhoff formula. Okay, and then we get rid of one variable to get back to 2D to get the Poisson formula. Okay, so that's how it goes. Let me now write things down a bit clearly so that you can see. Okay, let me now write back to even the equation 1 in again and equals to 2. So I would have the variable x would equals to x1 x2. Okay, let me write down, just put everything simply back to the so the equation 1 would be utt equals to Laplacian of u in R2 times 0 infinity ux0 equals to g of x on R2, and then ut of x0 would equals to h of x on R2. Okay, now as said, we now just introduce a fake new variable x3 so that we are in R3. Introduce a fake variable x3 in R so that yeah, and let me be consistent with the notes. I call it x bar equals to x1 x2 x3, or just simply x3 is going to be in R3, right? Because x is in R2 and we introduce another variable x3. And then we define u bar of x1, x2, x3, t to be just u of x1, x2, t. So, we lift everything by one dimensions. Um, x3 doesn't play any role here, right? Because u bar with x3, but it's equal to u without x3. So, but you see the advantage of this. And g bar of x1, x2, x3, t equals g of x1, x2, t. And h bar of x1, x2, x3, t equals h of x1, x2, t. So what's the point here? The advantage of this is that u bar differentiating x3 is equal to 0. Because, effectively it doesn't depend on x3, right? We just introduced that as a ghost variable. And similarly, you know, that I also have the g bar and h bar are independent of the variable x3. Okay, so that's the advantage of introducing this sort of fake variable. But this is important because you can see now that from equation 1, I have the equation, let's call it 1 prime, that u bar turns out to satisfy exactly the same wave equation. Why? Because you can see that u bar in x3 is 0, right? So the Laplacian in 2 variables is the same like the Laplacian in 3 variables. Because again, wait, let me write down and I'll explain. Okay, so I have u bar satisfy exactly this wave equation, but now in R3. And I have u bar x bar 0 equals to g bar x bar in R3 on R3, and u bar t at x bar 0 equals to h bar x bar on R3. Okay, so I have that. Again, everything looks the same, but I need to explain this here. This Laplacian. So here, Laplacian of u bar. Again, I lift one more dimension, the problem from 2D to 3D. So Laplacian of u bar of x bar t is equals to u bar at x1, x1. What? x1, x1 plus u bar at x2, x2 plus u bar at x3, x3. Okay, but this one is equal to 0. Okay, so this turns out to be exactly, because there's no such a x3 variable in u, right? So this equals to just u x1, x1, because u bar equals to u effectively, plus u x2, x2, which is exactly Laplacian of u in 2 dimensions. Okay, so again, we introduce a fact or a ghost variable to lift the problem from 2D to 3D. And in 3D now we can just use the Kirchhoff formula, right? So for the problem 1 prime, we use the Kirchhoff formula to get u bar at x bar t would equals to the integral on the sphere of center x bar radius t of the formula we wrote down earlier, right? So g bar of y bar, that's too many bars, but plus plus d times dg bar of y bar times x bar minus y bar plus d times h bar of y bar ds y bar. Okay, so we have this formula. And how do we get from here to the formula of u? Well, simply that, then simply add x bar equals to x and 0. I just let x3 equal to 0 to yield that u of xt equals to u bar of x0 at t, right? And this would equals to the integral on the sphere of center x0 radius t of this formula g bar of y bar plus t times dg bar of y bar dot with x bar minus y bar plus t times h bar of y bar ds y bar. Okay. That's one simplification I need to make, and then we get the Poisson formula. So there might be some confusion here because the point here is that we are taking a point x0. So this point is in the in the plane on this the plane of x3 equal to 0 on the 3 dimensions, right? And then here we are taking a sphere, and remember this sphere is in 3D. So this is why there's a computation. We take the sphere in 3D around this point. Okay, we take the sphere in 3D with the radius t. Okay, the sphere is taken in 3D. This is in x bar equals to x1, x2, x3, or simply x3. Okay, the integral we are taking is on the sphere. So sure, we can keep this formula, or the other way that we can do is that we can try to project this integral down to the circle inside here, the circle that I'm highlighting here, and you know, by doing this projection on the sphere to this circle, we can have the Poisson formula. I'm not gonna prove it because you know I'm gonna skip the proof of this formula because it's just a change of variable. Um, so you know, let me just write it down. So this is theorem 2. So wave equation in 2D in R2 with n equals to 2. This is a Poisson formula. Okay, you just simply project everything from the sphere to the circle to the disk here. Okay, I would let uxt equals to the integral projected down will become integral 1/2 the average integral on the ball of the ball in 2D. This highlighted ball here. Yeah, this is the ball. Of t times gy plus t squared times h of y plus t times dg of y dot with y minus x. Okay. Give me 1 second. I think I made a typo up here. Let me correct it. No, it's correct. Y minus x. Give me 1 second. Oh yeah, I made a typo here. It should be y minus x. I'm sorry about that. Yeah, because x is a center. Y minus x, y bar minus x bar. Yep, there's a typo here. Okay, that's why it's y minus x. Okay. Yep, this is correct. And then because I'm projecting everything down to this circle, I have to do some change of variable, and the change of variable results in this factor down in the denominator is t squared minus y minus x squared. This is clear because you know we were on the sphere, you know, we on the, yeah, let me write it down. I'll explain. To the power 1/2 dy. Okay, I have this formula. Let u equals to this, then you solve the wave equation in 2D. Okay, let me highlight it here and I'll explain just a little bit where did this term come from. Okay, let me draw another picture here. Is that I have this is the unit, so not the unit, this is this down here, or the this of center x0, radius t down here, right? This was the one that we highlighted, that we project everything on the sphere down to this. Okay, so we had a sphere up here and down here. Okay, for any point up here, so let's say that any point x bar up here, when I project it down to a point here, then this becomes you know, this becomes a point, this is a point y. Let me call this one point y bar. For any point y bar equals to y3 here, when I project it down, this is a point y down into this, you know, we just have the formula simply that y1 square plus y2 square plus y3 square equals to the radius square, which is t square, right? So y1 square plus y2 square is nothing but the length of y square, would be equals to t square minus y. Now let me write this way. Y square plus y3 square would equals to t square, right? So in other words, you can see that right away I have y3 would equals to t square minus y square. Okay, yeah, and okay, maybe let me, what I said here is, should I for simplicity I assume that the center is 0. Okay, so this explain that I have this term here and it's represent for exactly the term in the denominator here. Okay? Nothing more than that. All right, so now let me conclude by saying that you know, in the theorem 1, I made an important remark that what determines the value of u at a point is only the value of the initial data on a sphere around it, right? But in the second formula that I need to make a remark 2 is that for dimension 2 or even dimension in general, uxt is being determined by the value of g and h, not just on the sphere, but on the whole ball, on the whole disk, on the whole this, or the whole ball bxt. So it's determined by the information inside this whole ball instead of on the whole sphere. And this is a very important information. And this is, I can say that remark 1 and remark 2 tells us this is about the Huygens principle. Huygens principle says simply that for odd dimensions, and an example is n equals to 3, we do have sharp wavefronts, meaning that we have sharp wavefront, meaning that the information at UXT is solely determined by the information of initial data on the sphere of center X radius T, nothing else. But for even dimensions, writing, the case, for example, n equals to 2, then we don't have sharp wavefront. So no sharp wavefront, meaning that the information, the value of UXT is being determined by the whole initial data on the whole ball, so, anything changes within this ball give the change of the solution U at XT. Okay, that's all for the lecture today. Let me stop recording. How do I stop?